You know, we use electricity for everything. Flipping a switch, charging our phones, heating up dinner. It's so constant we barely even think about it. But what if I told you that a simple electric current has these hidden, almost magical powers? It can create invisible forces that shape our world in ways you might not expect. So let's uncover them. Okay, so let's set the scene. Imagine walking into a noisy, buzzing school science fair. Two students, Mohini and Akarsh, are just completely mesmerized by one of the projects. And no, it's not a model volcano or a Picado clock. They're staring at this little crane, but instead of a hook, it's just got an iron nail wrapped up in some wire. And with a simple flip of a switch, it picks up a whole bunch of paper clips, and then just drops them on command. Now here's the thing. There was no regular magnet anywhere, just a battery and some wire. And that's what sparked this huge question, not just for them, but for us, right? How on earth can a simple flow of electricity suddenly act like a powerful magnet? Well, the answer to that mystery starts with one of the most important discoveries in all of physics, really. It's this hidden link between two forces that people used to think were totally separate things. We are, of course, talking about electricity and magnetism. This experiment looks simple, but it's actually incredibly profound. So on the left, you see the circuit is off. The compass needle is just doing its thing, pointing north, like always. But now, look at the right. The second we turn that circuit on and current starts flowing through the wire, bam, the needle moves. It's actually being pushed by a new, totally invisible force. And that right there is what we call the magnetic effect of electric current. The bottom line is this. A wire with electricity flowing through it acts like a magnet. It creates a magnetic field around it, but, and this is the key, it's only temporary. The moment you turn the current off, poof, the magnetic field is gone. You know the crazy thing is? This wasn't some big planned discovery. It was a complete accident. Back in 1820, there was this professor, Hans Christian Ørsted, and he's in the middle of a lecture. He just happens to notice a compass needle twitching every single time he turns on his electrical gear. Just that one little moment of, that's weird, ended up changing science forever. It proved these two forces were connected. So Ørsted's discovery wasn't just some neat party trick. It was basically a recipe. It got people thinking, okay, if electricity can create magnetism, can we control it? Can we build a magnet that we can turn on and off whenever we want? And this is exactly what those students saw at the science fair. It's actually a pretty simple four-step process. You just take an insulated wire and wrap it tightly around an iron core, like a nail. Then you connect the wire to a battery. And just like that, that ordinary nail is now a magnet. But as soon as you disconnect the battery, it goes right back to being just a plain old nail. And that gives us our key invention, the electromagnet. It's exactly what it sounds like, a magnet made from electricity. Now, the coil of wire is what creates the field, but that iron core in the middle, that nail, that's the real game changer. It basically concentrates the magnetic field and makes the whole thing way, way stronger. Okay, so let's get back to our crane mystery. How was it so strong? Well, it's pretty simple, actually. You can totally control the power of an electromagnet. If you want to make it stronger, you can do one of two things. Either ramp up the electric current, add more batteries, or just add more coils of wire. And what's really cool is the level of control you have. You can even flip the north and south poles of the magnet just by reversing which way the current flows. But creating magnetic fields isn't electricity's only trick. Nope. There's another, super powerful effect that I guarantee you use every single day, probably without even thinking about it. And that's heat. It's a simple idea. Whenever electricity flows through a wire, it generates heat. You can kind of think of it like friction. All those electrons are bumping around inside the wire, and that creates warmth. Now, how much warmth you get depends on a few things: what the wire is made of, how thick it is, and of course, how much current you're pushing through it. And we have gotten really good at engineering this effect into all sorts of devices. For example, those glowing orange coils in an electric heater, that's just a special wire designed to get super hot when electricity runs through it. It's the exact same idea at work on your stovetop. That heating element is literally just turning electrical energy directly into heat to cook your dinner. Ever wonder how an electric kettle boils water so fast? You guessed it, it's got a powerful heating element right in the water, converting electricity to heat with amazing efficiency. And yep, even a simple electric iron works this way. Inside that flat metal plate, there's a heating element using the electric current to get hot enough to press your clothes. It is an incredibly common and useful application of this effect. Okay, so we've seen that electricity can create both magnetism and heat. But in all these examples, from the electromagnet to the kettle, where is that electricity coming from in the first place? Well, for that, we need to crack open a battery. The story of the battery is, well, it's fascinating and honestly a little bit weird. It all starts in the late 1700s with a guy named Luigi Galvani who noticed a dead frog's leg twitching when he touched it with two different kinds of metal. He thought the frog itself was making animal electricity. But then another scientist, Alessandro Volta, had a different idea. He figured, wait a minute, maybe it's not the frog, maybe it's the two different metals. And that key insight led him to invent the very first battery. And this is pretty much the basic blueprint he came up with. A voltaic cell is really just a tiny chemical power plant. You take two different metal rods, we call them electrodes, and you stick them in some kind of conductive liquid, an electrolyte. A chemical reaction starts up between the metals and the liquid, and that reaction pushes electrons from one rod to the other, creating an electric current. Now, this whole chemical reaction can go one of two ways. In your standard single-use batteries, that reaction is a one-way street. Once the chemicals are all used up, that's it. The battery's dead. But with rechargeable batteries, you can plug them in and use electricity from the wall to force that chemical reaction to run backwards. It basically resets the battery, so you can use it over and over again. So, we've kind of come full circle, haven't we? We started with a simple school project and ended up talking about the fundamental forces of nature. We've clearly seen how electricity can create magnetism. It seems like a powerful, but maybe a one-way street. Or is it? Maybe the connection between these two forces runs even deeper than we've seen so far. Our whole journey today started with this one core idea, that an electric current creates a magnetic field. And that leads to one last really big question. If electricity can make magnetism, could it work the other way around? Could a moving magnet create electricity? Now that's something to think about.